Hello, everyone. My name is Konrad Kamiński. I work for Allegro, so we're the largest Polish e-commerce company. And today I'd like to talk about coroutines and reactive programming. Because both of these solutions can be used to do some asynchronous programming. And it would be worth to see where we should use or where it's better to use one of either of those solutions. So I'm going to see a couple of, actually quite a lot of code where we'll compare both solutions and we can find out which one is better or what's the advantage of one over the other. And so what I want you to know after this session is when to use which kind of solution. And reactive programming, it comes in many forms. I mean, there are like many libraries available for reactive programming. So I had to choose one for this presentation. And I chose Reactor. I chose Reactor because it's quite a modern implementation of reactive library. It's gaining its momentum right now. It's like a backbone of the Spring framework, so like a major player in our industry. So I focused on Reactor, and also it has some nice features which are not available in other reactive libraries. So there is a very big difference if you write asynchronous code with coroutines and with reactive programming. So with coroutines, what you do is usually you write your code as if you would have written it in a regular way with some blocking calls. So here you can see a sample code, both with coroutines and reactive programming. And the main difference is that while with coroutines you see a regular imperative-style code, with reactive programming you have to restructure your code so that it's written more in a functional way. So you actually decompose your code into those independent pieces of code. And they are like lambda expressions for some of the operators available in reactive programming libraries. But there is also a bigger difference, because with reactive programming, you actually have two parts. So the first part defines the flow or the pipeline of operations that are going to be executed. And the second part is when you call subscribe. When you call subscribe, actually the whole machinery starts working. Whereas with coroutines, it's just the code executes one line after the other, we could say so. So let's start with some sequential code. This is where actually coroutines shine, so I want to put it at the beginning. So with sequential code, let's suppose you have a function which gets a user. It's an asynchronous function, so in the case of coroutines, it's a suspending function. And there is a second function that gets an account. It's a blocking function. And the parameters are either the user ID or the account ID. And if you want to create a function which returns an account number for a user with particular ID, then it's like very obvious. We just call one function and use the result of it as the input to the other. Now with reactive programming, you have to use one of the operators available on your reactive types. So here I use a reactive type called mano. So in the Reactor, there are two reactive types, mano and flux. So mano is like this stream of 0 or 1 value or an error. Flux is like a possibly infinite stream of values. But for now, we're going to use mano only. So the same thing with reactive programming. As I said before, you have to restructure your code into a functional way, and you have to use operators like map. And this is one of the problems of reactive programming. You have to learn all those operators, how they work, when to use what operator. With coroutines, you actually don't have to learn anything new. You just write your code the way you did before. So the question is, what happens like if you have a code like that and your function turns from being a blocking function to an asynchronous function? So in case of coroutines, nothing really changes in your code. The same code works as before. Now, what happens with reactive programming? So our function now our get account function no longer returns an account, but it returns a manner of an account. So actually we can't get the attribute from the result of get account. What we have to do is we have to use an operator, like a map operator. But now the problem is that the first map that we had there, it's a problematic situation. The code that you have here would return a mano of a string, and not a mano of a string as we want. And what we have to do is we have to use a flat map. Now, this is something which in the long term may be problematic. If you have an application and you don't know beforehand if your function is an asynchronous function or a regular function, then with coroutines, that doesn't really make much of a difference. With reactive programming, you have this problem that you have to not only change the signature of your asynchronous function, newly asynchronous function, but you have to also change the invocation of this function, the operators you use when you invoke this function. Now, we've seen sequential code, but asynchronous operations mean that things happen on different threads, because that's one of the advantages of asynchronous programming. You start processing something in one thread, and then you continue doing that on another thread where something happens, like when you get a response from a database or something. So the question is, can you somehow tell, in your code provide information about what threads we want the code to run? And actually, the answer is yes. So with coroutines, what we have to use is coroutine context, or especially coroutine dispatches. So the coroutine dispatches are these special kinds of coroutine contexts which have this ability that they can dispatch execution of a coroutine to a particular thread. So let's suppose that we want our getUser function to be executed in some specific threads, or we want to have a specific thread pool in which this function gets executed. And we want to create this thread pool by ourselves. We want to be able to control the number of threads that are in this thread pool. So we have to create our own context. There's a couple of functions in Kotlin standard library that allow you to create a new coroutine context with some thread pool, which would execute those calls, those coroutines. And one of them is new fixed thread pool context, where you specify that how many threads you want in that thread pool, and what should be the names of those threads. So in our situation here, what we'll have is we'll have a coroutine context with 5 threads, and those threads will have a name like user 1, user 2, user 3, etc. And to specify what context we want to use for a particular coroutine, we use a with_context function, where we pass as an argument the context that you want the code to be executed in. And this actually, we can use this with context so that one context is embedded or nested in the other. So if we have a situation where our getUsername function already is executed in some context, but we want, for example, to calculate an encryption key based on the name of the user, but it takes quite a lot of time because it's like CPU consuming. We want to limit the number of threads that are actually that will actually execute this function. We can use a different coroutine context. So we can create a separate one. Since those with context calls are nested, then getUsername will use one context, and getUser encryption key will use a different context. So just by nesting those contexts, we can achieve this architecture of applications where we can say what kind of code or where it should be executed. And the same thing actually is possible with reactive programming. With reactive programming, what you can specify is, on one hand, when should the source of your whole pipeline, where should it start being executed? And you do it with the subscribe on operator. With reactive programming, or generally with Reactor, the equivalent of a coroutine dispatcher is a scheduler. And you can also create your own scheduler, where you specify how many threads this scheduler should have, and what should be the names of the threads that are in this scheduler. So the concept is quite similar, but the difference is that if we used subscribe done to specify where this pipeline should start. But if we want to specify what scheduler should be used for the code, which executes some operations after a certain point, we have to use publish on. So there is like this duality here. But other than that, the model is quite similar. Now, our functions, they may be executed in many threads. And the nice thing about a single-threaded model is that you can use things like thread local. With thread local, you can assign a variable. You can set a variable to some value. And this variable is actually sort of attached to a thread. So wherever in your code, when it's executing in some thread, you can actually read and write that variable. So it would be nice to actually be able to do the same thing with reactive programming or with coroutines, but we have like different threads of execution. So the question is, how can we achieve that? So with coroutines, what we would like to have is, like in this example, we have thread local variable. We would like to be able to read this variable in some function so that we can, for example, put in the log output the request ID of an incoming request. So we set this request ID at the beginning of the processing of some request, and later on, in some function, we want to actually retrieve it so that we can put it in the log files, so that we can then trace the execution of that request. So how can we achieve that? We obviously have to invoke the logging get user function in our example so that it gets logged. But there is one thing missing, and this is with context. So we've seen before that we can use context for specifying what threads, or for specifying a coroutine dispatcher. And we've also seen that these contexts can be nested. And in fact, we can create our own context, which will have this functionality that it will take the value of a thread local upon call to with context. And once the execution of that, the lambda that is passed as a parameter of this with context, once it's executed on any thread or it switches the threads, the thread local will be restored to the value of the thread local that was set at the time we actually invoked this with context. So it doesn't really work like 100% the same way as it does like with regular threads, because normally you can also set this value. Here, it's sort of like a thread local read-only value. So you set it once, and then it's propagated to every coroutine that's being created in that context, directly or indirectly. And with reactive programming, or essentially with Reactor, and this is actually one of this is actually why I chose Reactor, because Reactor is actually the only, at least known to me, reactive library which has this sort of behavior, this sort of functionality that allows you to create a context and allow it to be propagated from the time you call subscribe, to through the whole pipeline. So how do we do it with Reactor? We obviously would want to have a code like this, where we would be able to use thread locals directly. But actually, that's not how it's done with Reactor. With Reactor, we have a special subscriber context, where you can access it at any time in your pipeline with the subscriber context static method, and then use it in your operations. So when and how do we actually set the subscriber context, and how does it look like? So it's actually sort of like a map. There's like a key and a value, and the way you use it is you actually call subscriber context on your reactive type, whether it's mono or a flux, it doesn't really matter, and you provide the initial context that will be propagated through the whole pipeline. So in our example here, you can see that we set this request ID. We actually get the value from the thread local. The important thing is that this value will actually be taken at the time you call getUsername, not at every time this mono is subscribed to. And with that, we see that we have a similar functionality. It is a bit different in terms of how you write your code, how you structure your code. But other than that, it's quite similar. So you are able to actually have this request context. The code we've seen so far, we actually there was only like a happy scenario path, like everything worked. But in the real world, not everything works correctly all the time. So there are exceptions thrown sometimes, like, there is, with asynchronous programming, if you want to fetch some data from some other server, you have a network exception. You have to handle it somehow. So how do we do it? With coroutines, we use regular language constructs. We just catch the exceptions and do whatever we want to do. So in this example, we just return some default value. With reactive programming, of course, we have to use some special operator. In fact, there's a couple of them, and we have to know beforehand which one we want to use, because there are different scenarios where we would want to use one of them. So, for example, the on-error return that is shown here, we provide like a default value that will be returned if there's an exception thrown. So we can also use things like on-error resume or on-error map. On-error resume will allow you to actually, it takes as a parameter a mono, so it will allow you to dynamically somehow say, what should be done. On-error map will map the exceptions coming in and out of this mono. So here, again, we see some differences because of this functional way of writing your programs. Now, if there are exceptions thrown and we have asynchronous calls, then we sometimes want to retry the operation. Because, the network is unreliable. We may want to invoke or access an external endpoint. The network may be dead for some time, or our server on the other side may not work for some time, but we want to retry a couple of times before we say, OK, so it doesn't really work, and we can't really do anything about that. So the important thing is to be able to retry operations. And with coroutines, again, we can use simple Kotlin language, where we can try to invoke an operation in a loop. And if there's an exception thrown, there's a counter in that loop. If an exception is thrown and the counter is below some value, some limit, then we just retry after waiting for some time. This is why you see this delay here. So delay is the function, the suspending function, not a blocking function, but a suspending function. We just wait for some time. So the policy implemented here is that the first time there is an exception, we wait for half a second, then we wait for a second, etc., up to 5 times. And if all 5 calls fail, then we just throw the last exception that was thrown by the get user. So the code is quite straightforward. In fact, what we would do normally is we would somehow extract that retrial logic into a separate function so that we could reuse it in some other places in our code, in our application. And that's actually quite simple. We can define a retry function which takes these 3 parameters, how many times you want to retry, what's this minimum time you have to wait before calls, and the function that could fail itself. And now our code will look a lot better, a lot simpler. Now, obviously, reactive programming guys thought about this scenario too, because they provided a couple of retry operators. And obviously, you also are able to create your own policy of retrying. And the way it's done is, it's not quite non-intuitive. I mean, after you learn it, maybe probably, for me it wasn't. But, so there is this retry when operator where you provide a function, but this function has a special signature. It takes as an input a flux, and it also, as an output, returns the flux. So the input is a flux of exceptions, of throwables actually, and the output is a flux of long values. And the contract is that the flux of throwables, it actually represents the exceptions that are thrown in the upstream of your whole pipeline. And this output flux, it actually tells the whole machinery whether we should retry, meaning we should resubscribe, or whether we should just stop retrying. And the flux is, like I said, it's like possibly infinite stream of values. So in a way, it's similar to a sequence of values, but there is this timing factor, so the values may come at certain points in time. So by returning a flux of long and having this time factor, we can actually say when this retrial should happen. So let's try to define a function similar to the one that we've seen just before for the reactor. Yeah, so that's the function. I will not actually go over this function. You can make a photo or something. That's quite complicated, but it works. I can assure it works. So it provides a proper flux with the policy that we want to have. So in a way, it's similar to coroutines, but then again, if you want to create your own policy, which is somewhat complicated, you will have to spend some time doing that. Fortunately, there are libraries available with different kinds of policies where you can just grab a function, pass the parameters, and it will work. It's just that if you want some special policy, you usually have to write this kind of stuff yourself. So far we've seen a sequential code, and in sequential code, this is where Kotlins shine because they were designed for sequential code to look very nice. But oftentimes in our applications, we have concurrent code. So with concurrent code, you have a couple of operations which have to run concurrently, and then at the end, you want to gather the results of all of those operations and do something with them. So how do you do it with coroutines? There is a function called async. It's actually an extension function of a coroutine scope. We're going to talk about coroutine scope a bit in a moment. And this async will actually launch a coroutine in the background thread, and this coroutine will start running. And at some point when it finishes, it returns some result. And the result is actually wrapped in an object called deferred. So deferred is sort of like a promise type object. So if you've ever worked with any promise type libraries, it's very similar. So what we do if we want to invoke two operations concurrently is we call async twice. That would start executing both coroutines concurrently. And then we wait for the results. So we call await. Await will, it's a suspending function, so the whole coroutine will suspend until the result is available. Now there is this coroutine scope thing. A coroutine scope, there was a great talk today by Roman Elizarov about coroutine scope, so I'm not going to repeat that. But actually it allows you, what it does in here is that whatever coroutines are created and executed in this coroutine scope, they have to finish before we actually finish this whole function, this whole suspending function. So even if we have some exceptions thrown during the execution of either get user or get roles, the whole thing will work properly. And there's one more important thing about coroutine scopes. So imagine that the get user function, it takes quite a long time to actually execute. But the get roles functions is quick and it fails. It fails almost immediately, so it throws an exception. So in our code, we first call await on the user. So we would wait a long time to get that user, only to call await on the roles to get the exception. That's not a nice thing. What we would like to have is to get that exception as soon as we can. And this is actually what coroutine scope is also used for. So those two coroutines created with async are children of this coroutine scope. And if any of the coroutine fails, then the coroutine scope will cancel all the rest of the coroutines. So if our get roles fails, then it will try to cancel the coroutine that executes get user, which means that if there is some very nice cancellation policy, the wait on the user will at that time return an exception. So that's a very nice property. And with reactive programming, it's very similar. We have a zip operator. A zip operator takes a couple of monos or fluxes, if you use flux, and it waits for those monos to complete, and then it can invoke a function with the results of those monos, so that you can you can invoke your business logic or any kind of logic on those results. And so if you look at the code, and actually it has also this nice behavior of canceling or disposing of the mono. If one of the mono fails, the other ones are canceled as well. So it has the same nice property as coroutines. So the code looks here a bit better than the one with coroutines. So I started to wonder, that in this situation is probably I would use reactive programming, but let's just imagine a different scenario, a more complex one, but not that more complex. And it will also be something worth to know about cancellation. So imagine that, we have the same code as before with just one change. So imagine that a user may be blocked or maybe not blocked. And if a user is blocked, then we actually don't care about the roles, because we will just want to return the empty roles. So what it means is that if we have, if the coroutine that returns the user data, when it finishes and we have this data about the user and we know that he or she is blocked, then we may cancel the execution of the roles because we are no longer interested in this, what roles are actually this user have. So what we can do is we can await only on the coroutine. So we can start both coroutines concurrently because we want the roles to execute quite fast. So we could wait for the user coroutine to finish and then only starts the one with roles, with get roles. But that would, in total, it would take a long time. So we start them concurrently. And when the user is blocked, then we just cancel the coroutine, which gets roles, and we return this empty roles for that user. Otherwise, we'll just wait for the roles, for the coroutine to be finished. So we changed the code a bit. It's not that more complex. I have a problem with reactive programming version of this code. I actually asked a couple of people. I got some responses about, because I tried to write it on my own. It was quite hard to do. I asked some smarter people than me about that. They came up with different versions. So this is actually similar to one of the versions. I'm not sure if it works in every possible situation. So if you know any simpler code, for that, then just let me know. I'll be happy to actually see how it can be done. But obviously, you can see that it is quite complex. So for simple things where you don't care, like you don't have this scenarios where you want to cancel things before finishing the whole stuff, you probably the code with reactive programming is a bit simpler. But if you want to handle more complex scenarios, then coroutines are a bit better. So how about some parallel code? So we've seen concurrent code. Parallel code is when you want to invoke the same function for different input parameters. Like, for example, you have a function which returns a user IDs for some account, and then you want to write a function, and you have a function which returns a user for a particular ID, and you want to have a function which returns a list of users for an account, and you have only the ID of that account. So how do you do that with coroutines? Again, this is pretty straightforward. You get a list of user IDs. Then, for each ID, you create a coroutine. You do it with async. So you start as many coroutines as there are users. And then you can invoke a nice function which is called await all, which actually it's a pretty simple function. It will go over that list, and for each of the deferred that is inside that list, it will await for the result. And once all results are available, it will just return that list. Again, we use coroutine scope here in case any of the coroutines fail. So with reactive programming, we can actually do a similar thing. So here I use a mano of a list, which means that the function will return the whole list at once. And to be able to do a thing which is a counterpart of the code with coroutines, I have to first convert it from a mano of a list to a flux, then do a flat map, and then get back from a mano of a list, from a flux to a mano of a list. So normally, really, we wouldn't have done it that way. We would just use a flux of ints or users. So the code right now is a lot more simpler. So we've actually covered quite a lot about manos. Now there is this flux thing. So a flux, like I said before, it's like an infinite, possibly infinite, or it can be finite, stream of values which has this timing factor. And there is a similar concept in coroutines, similar to flux, and it is channels. So if you want to have a function which returns a list of users, or a sequence of users, generally users, what we could have is a function which returns a receive channel. So channels are like different kinds. A receive channel, it allows you to only receive values from a channel. There is also send channel, which allows you to send values to channel. There is also a channel itself, which is both send and receive. The important thing about sending and receiving from channels in coroutines is that these functions are suspending, and it has actually quite nice consequences. Because we can see here a code which just receives values from a channel. So we want to print all the users for a particular account ID. So we get the users as a receive channel, and then we loop receiving the values from the channel, and we print the values, the names of these users. Now, channels can be closed at some point in time if, like, we have nothing else to send to a channel, we just close it. And in that case, the receive will fail with an exception, so that's really not nice. What we could do is we could use a different function, which is called receive or null, where it will return a null value in case the channel is closed. In that way, we could nicely have this loop. And in fact, it's such a common pattern to actually go over all the messages from a channel that there is a special extension function called consume each, where when you call it on a receive channel, you can provide a lambda which will be invoked on every message of that channel. So I mentioned that there is important thing about the send and receive channel, because the send and receive functions are both suspending functions. And the way it works is that if you send a message or you invoke a send function, you want to send a message to a send channel, and there is no receiving side, there is no one which calls receive, then your send call will actually be suspended. So it will wait for someone to be receiving on the other side. And by the same token, if you want to receive something from a channel, but there is no sending side, then the receiver will wait until there is someone sending this value. So there is this, it has like this very nice property where if a sender wants to send a lot of messages, it has to actually wait for someone to get those messages. You can't really send 100,000 of messages and don't care about whether there's anyone listening. So we'll get to that later on when we talk about backpressure. Now with reactive programming, there's like many ways to express the same kind of code. What we usually do is we call subscribe, which executes the whole machinery, the whole pipeline, and we can provide a lambda which will actually get all the values from this flux, this stream of values. So how do we generate such streams? With coroutines, what we can do is there should be a send channel there, not a receive channel. There's a mistake. So, it could be a receive channel as well. Yeah. So what we do with coroutines is we create a channel with a channel function. And so channel is both a receive channel and a send channel, so we can use it both to return it as a receive channel and to send the values to this channel. We send the values using send functions, and we close the channel using close, obviously. So what we do here is we launch a new coroutine, and that coroutine will send some values, and then we close the channel. And then we can use a different kind of extension function which combines both of these things, meaning the creation of a channel and being able to actually use send functions to send to that channel. And it's called produce. So we can use produce. It actually does the same thing as the code that you've seen before. With Flux, there is like multiple options to create fluxes depending on whether you want to create Flux and send the messages to Flux in multiple threads or in just a single thread. I use generate. It's like the basic one, which allows you to specify a lambda where you just call functions on a sync. And when you call next on a sync, that value will be delivered to this stream or this stream. The important thing that it's not actually, you actually can't see it from the code here, but like I said, with Flux or with reactive programming, you have these two parts. First, you define a pipeline, then you subscribe, and only if you subscribe, the whole machinery starts being executed. Now, this is not the case with coroutines. If you call produce here, then that produce will actually launch a coroutine, and it will start being executed. So it will actually call send. With Flux, this lambda here will not be executed until you call subscribe. So this is something, the difference is because there is a concept of a hot stream and a cold stream. So a hot stream, in hot stream there is always like a producer doing something, and if you subscribe to it, you just get the values from that point in time. With cold stream, when you subscribe to it, it then starts doing something and producing those values. So in that sense, the receive channels or channels in Kotlin are hot streams. They are hot channels because when we call produce, it already starts running. And it doesn't wait for the receiving part, for the other side to receive those values. So this is the major difference. And actually, there is some work being done right now to provide also cold streams for coroutines as well. Now, both receive channels and flags have operators, but there is this difference in how they are executed. With coroutines, if you have an operator like a map, what it will do, it will create a coroutine which will take a value from a receive channel, create a new channel. I mean, it will first create a new channel, and it will take the value from the receiving channel, and it will somehow transform it. So in the case of map, it will call a function, and the result of that function will be sent to this output channel. So you have this active process, this active coroutine running all the time, receiving value from one channel and sending value to the other channel. With reactive programming, it's a totally different thing, because if you call map, nothing really happens until you subscribe to the whole pipeline. So this is the major difference. And you can create your own custom operators. So in reactive programming, it's usually said that it's quite hard to create new operators. With coroutines, that's quite simple. Like, let's suppose you want to have an operator called filter map, which takes a function that when it returns a value, a null value, we don't want that value to be returned in the output channel. And if it returns a null value, then we just send it. The code for such a function, it's quite simple. I'm not going to provide the code for the reactive programming version because, well, on one hand, I'm really not able to write such a code. On the other hand, I've actually looked at the code of the map and filter in Reactor, and it's like several hundred lines of code. So that's quite too hard for me. So I mentioned that with channels, you have the sending side, the receiving side, and the sending side will wait until there is a receiving side, and the receiving side will actually wait before someone sends some value. So that's something which is called backpressure. With backpressure, the sending side will have to know if it can send more values, so that the receiver will not be overwhelmed with too many messages. And with the code that I've shown you, which produces a channel, which creates a channel, we use this channel function. And this function actually takes some parameters there's one parameter in that function which describes what kind of channel we want. So the default one is called rendezvous, or I'm sorry, my French is not that good. So it's called a rendezvous channel. And it works, like I said, the sending part waits for the receiving side, etc. You can specify an int, which will say, how many messages you want to be buffered before the sending side is suspended. So if you provide 5, it means that you can call send 5 times. And if you call it for the 6th time, only then it will be suspended. So you can, even if there is no receiving side, you can easily send 5 messages. The unlimited is unlimited, so the buffer is unlimited. You can send as many messages as you want. Of course, you have to be aware that you may get an out-of-memory error at some point because they are buffered. And there is a special one which is called conflated. And conflated means that the receiving side will always see the last value that was sent by the sending side. So you may miss a couple of messages if you're slow. And the same thing actually can be done with reactive programming. There you can specify what kind of backpressure strategy you want to use. And there are some similarities between the available strategies and those kinds of channels that are available. So we've seen the code with coroutines and reactive programming. The question is now, sometimes one is better, sometimes the other is better. Can we somehow combine both of them? So there are ways to actually use coroutines with reactive programming code and the other way around. So for example, if you have a function which returns a mono, and you want to use it in your coroutines, you can easily somehow transform mono to a suspending function. So we call await first or null, which will actually wait for the value. And if there is no value, so the mono is empty, it will just return a mono value. And there's a couple of more of these kinds of functions. There is await first, which will wait for the first value, so it will not accept the empty monos. And there are some other functions as well. And you can also do the same thing the other way around. If you have a suspending function, but you have an API which actually wants some reactive types, you can create, you can use mono function where you pass a lambda, a suspending lambda, so you can use suspending functions in that lambda, and it will provide a mono for you. The same thing applies to Flux. So for Flux, if you have a Flux, like a stream of values, you can call open subscription. It will give you a receive channel so that you can use this channel in your coroutines. And by the same token, if you have a receive channel, you can create a Flux where you send some values to this Flux. So the question is, which one should we use? So there's like no specific answer to that. It always depends on the use case you have. I mean, clearly in the sequential code, coroutines will shine because they were designed for sequential code. If you have a few methods, a few functions you have to call one after the other, then obviously it's easier to read and write with coroutines. Concurrent code, it only depends on what use case you have. Sometimes it's easier with reactive programming, sometimes it's easier with coroutines. You have to be aware that channels are actually still experimental. So while the part about monos, those suspending functions, async, launch, etc., it's stable, receive channels are still experimental, and they may change because of this because they, at some point in time, cold streams will be available, and so we don't know yet what the final design will be. And at the end of the day, you actually can mix both solutions because of this interoperability between both of these of the approaches and the availability of the functions, which allow you to create monos or coroutines from one from another. If you want some more information, there are two documents which are worth reading. The first one is actually focused on reactive programming, the guide to reactive streams with coroutines, a very nicely written document. So if you're interested in this topic, I suggest you to take a look at that. And coroutines guide, that's like a general coroutines guide, but it also has some nice parts about these things I talked about. You can have a look at that as well. Okay, so thank you very much. And if you have any questions, I think I'm out of time, so you can talk to me after this talk.